The Diffusion Transformer, DiT, is an innovative approach that combines two powerful technologies, diffusion models and transformers. Both of these are state-of-the-art techniques in machine learning, and the DiT model integrates them to improve image generation. Let's explore it in 4 parts. The Diffusion Transformer architecture. What are the advantages of using transformers over U-Nets in diffusion models? What are the main differences in feature fusion between DiT and U-Net architectures? The role of Adaptive Layer Normalization in DiT. Now let's break down the Diffusion Transformer architecture step by step. The first. Background, diffusion models and transformers. For diffusion models generate images by starting with random noise and then gradually denoising it. The process has 2 parts. 1. Forward diffusion. Noise is added to the image step by step, starting from a clean image. 2. Reverse diffusion. The model learns to reverse this process, removing the noise at each step to recover the original image. The model is trained to predict the noise at each step and remove it. For transformers. Transformers are deep learning models that use self-attention mechanisms to capture relationships across all elements of a sequence. For images, this means understanding how different parts of the image relate to each other. A key feature of transformers is their ability to handle global context, which is important when generating high-quality images that require global consistency in structure and content. Unlike CNNs, which focus on local regions of the image, transformers can capture global context, which is especially useful when generating complex images with coherent structure. The second. The DiT architecture. The DiT model merges diffusion models with transformers to enhance image generation. Here's how it works. 1. Input representation, for positional embeddings. Since transformers don't inherently understand spatial relationships, like where one pixel is in relation to another, we add positional embeddings to the input. This helps the transformer know where each image patch, or segment, is located in the original image. For image tokenization. Just as words are tokenized into smaller units in text, the image is split into patches. Each patch is treated as a token and passed through the transformer. 2. Forward diffusion process. In this step, the process of gradually adding noise to the image over time is controlled by a noise schedule. This schedule determines how the noise level increases as we move through different time steps, or diffusion steps. The forward diffusion process takes an image and progressively adds noise, starting from a clean image until it becomes a completely noisy image. The model learns how to reverse this process during training. 3. Transformer encoder. The transformer encoder processes the noisy image at each time step, using self-attention to capture the relationships between all image patches. For multi-head attention. Multiple attention heads are used to capture different features of the image, such as texture, color, and structure, for feed-forward networks. After attention, the features are refined through feed-forward networks to better represent the image content. For adaptive layer normalization. This is a key innovation in DiT. AdaLN incorporates conditional information, like noise time steps, class labels, or even text, to modulate the activations before residual connections. This helps the model handle varying conditions during training and inference. Essentially, AdaLN layers adjust the behavior of the transformer blocks based on additional information, making the model more flexible and adaptable to different conditions. The layers are initialized to act as identity functions, which means they start with no effect and learn to incorporate the conditional inputs gradually. 4th, reverse diffusion process. The core of a diffusion model is the reverse process, where the model learns to reverse the forward diffusion process. This is where the transformer's power comes into play. Instead of just denoising pixel by pixel, DiT applies a global understanding of the image through self-attention to iteratively recover the clean image. At each step of the reverse process, the model learns to predict the clean image from its noisy version. This requires the model to learn how different image patches correlate and how to reconstruct them from noisy versions. 5. Decoder, image generation. Once the noise is removed, the model uses a decoder to convert the clean, denoised representation back into an image. The decoder could be another transformer block or a simpler network that translates the refined features back into pixel space. After processing through all the transformer blocks, we need to decode the final output. The output feature from the last block is decoded. A noise prediction, which helps in generating a cleaner image. A diagonal covariance prediction, which provides a measure of uncertainty about the noise. A linear layer decodes each patch token into a tensor of size p multiply 2c, where c is the number of channels. Finally, this tensor is rearranged back to match the original spatial input shape to reconstruct the image. The third. Training the DiT model. The model is trained using a technique called denoising score matching. The training objective of DiT is to minimize the difference between the generated image and the original clean image during the reverse diffusion process. Specifically, it learns to predict the noise added at each step of the forward diffusion process. The model is trained by comparing the predicted noise with the actual noise added to the image at each step. Common loss functions used in diffusion models include L2 loss, mean squared error, or Kullback-Leibler, KL divergence, which measures the difference between the predicted distribution of noise and the true noise distribution. In summary, diffusion transformers combine the power of transformers to model long-range dependencies with the generative power of diffusion models, leading to high-quality image generation. Now let's explore the key reasons why the transformer decoder in Diffusion Transformer is a better choice than the traditional U-Net decoder for image generation, particularly when it comes to handling high-quality image generation and incorporating conditional information in a flexible way. The first. Global context and long-range dependencies. For transformer decoder, DiT. The core strength of the transformer decoder lies in its ability to attend to the entire image simultaneously using the self-attention mechanism. This means that every patch or token in the image can interact with all the other patches, allowing the model to capture long-range dependencies. For example, in an image generation task, the model can understand the relationship between distant objects, like a tree in the sky, creating a more coherent image where all elements are integrated seamlessly. For U-Net decoder. On the other hand, the U-Net decoder relies on convolutions and skip connections to fuse features between the encoder and decoder. This works well for capturing local dependencies, details within smaller regions, but it struggles with long-range relationships. This means that U-Net might struggle to maintain global consistency in tasks where larger context is important, such as generating images from text where distant parts of the image need to relate accurately to each other. The second, flexible and dynamic conditioning. For transformer decoder, DiT. One of the key advantages of transformers is the cross-attention mechanism, which allows the model to dynamically adjust its focus during image generation. This is especially important when dealing with conditional inputs like text or labels. In text-to-image synthesis, for instance, each image patch can attend to relevant parts of the conditional input, such as specific words in a description, ensuring that the generated image aligns well with the input context. The model can adjust its focus on different parts of the text as it generates the image, leading to a highly adaptive generation process. For U-Net decoder. U-Net, in contrast, typically injects conditional information through concatenation or addition at certain layers. While this method works for simpler conditions, it is more static. Once the conditional input is fused into the model, it doesn't allow for the same dynamic adjustment that transformers do during the generation process. This static approach can limit the model's ability to refocus on different parts of the conditional input at different stages, reducing the flexibility of how the input influences the image generation. The third, better handling of complex conditional inputs. For transformer decoder, DiT. Transformers excel at handling complex high-dimensional inputs like text descriptions, multimodal data, or structured information. The cross-attention mechanism allows DiT to integrate these rich, high-dimensional features effectively into the image generation process. For example, in text-to-image generation, DiT can use the text's semantic content to directly influence the generated image, resulting in better alignment between the input and the output. This makes it particularly well-suited for tasks requiring detailed interpretation of complex, structured inputs. For U-Net decoder, U-Net's method of injecting conditional information through concatenation or addition is more restricted. While it works well for simpler inputs like class labels, it can struggle with tasks involving complex or high-dimensional inputs, such as text or detailed embeddings. This limits its flexibility in handling sophisticated tasks like text-to-image generation. The fourth, scalability with input size and resolution. For transformer decoder, DiT. Transformers, including the decoder in DiT, perform better when handling larger input sizes and higher image resolutions. The self-attention mechanism, although computationally intensive, scales well because the image is divided into smaller patches, tokens, allowing the model to handle larger images efficiently. This patch-based tokenization also allows DiT to process fine-grained details in high-resolution images while maintaining the ability to model long-range dependencies across the entire image. For U-Net decoder. U-Net, with its reliance on convolutions and skip connections, can face difficulties when scaling to very high-resolution images. The feature maps produced by convolutions grow larger as the resolution increases, leading to memory limitations and slower training times. As the image size grows, U-Net becomes less efficient, and computational costs rise, especially when handling very high-resolution images or large datasets. The fifth, better capture of fine-grained details with global context. For transformer decoder, DiT. The self-attention mechanism in DiT enables fine-grained details to be captured while maintaining global coherence. Each patch, token, interacts with all other patches, so small details can be refined within the broader context of the entire image. For example, when generating a scene with both small objects, like a car, and large background elements, like a city, the transformer can ensure that the small objects fit seamlessly within the larger scene, preserving both local details and global consistency. For U-Net decoder, U-Net excels at local refinement through convolutions, but without the global attention provided by transformers, it might miss the broader contextual relationships between distant parts of the image. For tasks where global consistency is key, U-Net may struggle to maintain these relationships. For instance, in a complex scene, U-Net might have difficulty ensuring that small objects, like clouds, align consistently with distant parts, like mountains, without additional modifications. The sixth, reduced computational complexity for large-scale contextual generation. For transformer decoder, DiT. While the self-attention mechanism in transformers can be more computationally expensive than convolutions, it is often more efficient when handling large-scale dependencies. By dividing the image into smaller patches, transformers reduce the computational burden, allowing for more efficient global context modeling. New advances in efficient transformers, such as sparse attention mechanisms or techniques like longformer, further improve scalability, enabling DiT to handle complex tasks and large images more effectively. For U-Net decoder, U-Net's reliance on convolutions and progressively larger feature maps results in higher spatial complexity as the model deepens. As the input size grows, so does the model's memory and computational requirements, which can slow down training and inference times. In summary, the transformer decoder in DiT offers significant advantages in tasks requiring global coherence, dynamic conditioning, and the ability to handle complex inputs like text. It excels in text-to-image synthesis, where long-range dependencies and contextual alignment are crucial for generating accurate images. The U-Net decoder is better suited for tasks that focus on localized refinement and multi-scale feature fusion, such as image segmentation, where fine details are essential but global consistency is less of a concern. Now let's explore how diffusion transformers, DiT, and U-Net architectures differ in their approaches to feature fusion in diffusion models. The first, fusion mechanism, for DiT. 1. Adaptive Layer Normalization, AdaLN. DiT uses AdaLN to combine conditional information with features dynamically at every transformer block. 2. Cross-attention. This mechanism enables interaction between the diffusion model and an image encoder, mixing embedding sequences efficiently. For U-Net. 1. Skip connections. U-Nets use direct skip connections to pass feature maps from the encoder to the decoder. 2. Concatenation and convolution. After concatenation, convolutions are applied to merge features from different scales. The second. Feature processing. For DiT, processes inputs as patches. These patches are flattened into a sequence for processing, giving DiT more flexibility in handling data structures. Enables dynamic conditioning throughout the model, adapting to complex inputs. For U-Net, maintain spatial structure. U-Nets use convolutional layers to process the entire image while preserving its spatial integrity. Combines low-level details from early layers with high-level abstractions from deeper layers using its U-shaped architecture. The third. Scalability and flexibility. For DiT, highly scalable. Performance improves as the model size and the number of input tokens increase, making it ideal for large-scale tasks. Task adaptability. Works well with diverse tasks, including multimodal applications. For U-Net, moderate scalability. To scale, U-Nets typically increase the number of channels or layers, which may require significant architectural adjustments. Struggles with tasks involving complex conditions or multimodal inputs without modifications. The fourth. Semantic gap handling. For DiT, uses transformer blocks and self-attention mechanisms to capture relationships between different parts of the image, potentially reducing the semantic gap between encoder and decoder features. For U-Net, significant semantic gap. The difference between encoder and decoder feature representations can grow in deeper layers, potentially affecting performance. Advanced variants. Some U-Net versions, like U-Net++, add convolution layers in the skip pathways to better align features. In summary, DiT offers flexible, scalable, and dynamic feature fusion using AdaLN and cross-attention, making it suitable for complex and multimodal tasks. U-Net, with its skip connections and spatial processing, excels in preserving image structure, but may face challenges with adaptability and the semantic gap in deeper layers. Each architecture has strengths tailored to different use cases, but DiT stands out for modern, large-scale diffusion tasks. Now let's break down the role and importance of Adaptive Layer Normalization, AdaLN, in the Diffusion Transformer model, and understand how it enhances performance and enables efficient conditioning. The first. Conditional information injection. AdaLN is the primary mechanism for incorporating conditional information into the DiT model. Here's how it works. AdaLN allows the model to use external inputs such as diffusion timesteps, class labels, or text embeddings. These conditional inputs are used to generate scale and shift parameters that modify the input sequences at each stage. These adjustments help the model learn to generate images that align with the provided conditions. The second. Integration in transformer blocks. AdaLN is tightly integrated into the transformer blocks of the DiT model. It applies modulation to the activations before the residual connections within each transformer block. This ensures that the model can adapt its behavior based on the condition at each step of the image generation process. Essentially, the model learns to respond to the given condition, like text or labels, as it moves through the layers. The third. Improved performance. The use of AdaLN greatly contributes to the performance of DiT models. AdaLN is shown to be more effective than other conditioning methods, such as cross-attention or in-context conditioning. DiT models with AdaLN consistently achieve state-of-the-art results on image generation tasks, outperforming earlier diffusion models by a significant margin. The fourth. Computational efficiency. AdaLN provides a computationally efficient method for integrating conditional information. It only increases between 10% and 20% of the total parameters of the model. This relatively small increase in parameters allows the model to achieve substantial improvements in performance without a significant computational overhead. The fifth. Initialization and training. AdaLN is initialized in a way that improves model training. Initially, the transformer blocks are set up to behave as identity functions, meaning they don't modify the inputs at the start. This allows the model to begin training from a stable state and gradually learn to use the conditional information, making it easier for the model to adjust as it trains. The sixth. Adaptability. Across denoising stages. One of the key advantages of AdaLN is its ability to allow the DiT model to adapt throughout the denoising process. As the model goes through different stages of denoising, AdaLN helps it focus on the relevant features for each step, guiding the image generation in the right direction. This adaptability ensures that the model can refine its output progressively, leading to higher quality, more contextually accurate images. In summary, AdaLN is a core component of the DiT architecture, allowing the model to efficiently incorporate conditional information into the image generation process, improve performance by using a flexible adaptive mechanism, maintain computational efficiency with only a modest increase in parameters, adapt across different stages of the denoising process, resulting in high-quality images. AdaLN significantly enhances the flexibility, scalability, and performance of DiT models, making them particularly effective for complex image generation tasks.